Any questions before we get rolling? So. So I know that's kind of my default thing, but I emphasize that here, theorem. Are number one, this is called Hilbert Basis Theorem. There are theory. So is R of X. And two, if R is a theorem, so is R power. Now, last time I pointed out an interesting converse sort of this due to Gilmer, and that is if Rx is Noetherian, then this implies that R is Noetherian and it has identity. So for Rx being Noetherian, it's necessary that it has an identity. And this is true for our power X. And I give an example that sort of illustrates this. But here on out, I'm going to assume that R is community one. And what I'd like to pay attention, so let's sketch it further. Suppose R Noetherian and when A and Rx. So it suffices to show, if you want to show that Rx is Noetherian, it suffices to show that it's finitely generated. Any ideas on how we might do this? Right. So any ideal down in the coefficient range, sure enough, they're all finitely generated. But what if we had something more complicated in the polynomial range, for example? So let's consider the following. The following. Let's say given A. So for all n greater than or equal to 0, we consider the following ideals An. An is the ideal generated by P of X, and A such that degree P of X is less than or equal to n, or p of x is 0. Right, so I haven't really defined the degree of zero polynomial, so. So, for example, what we have is A0. This is generated by all the constants in the ideal. Now, of course, there may be no constants other than 0, right? For example, let me give you a silly example. Suppose that this is a neutral domain and A is a principal ideal generated by an 11th degree polynomial, right? Then there are no linears, there are no constants, there are no quadratics. So this will all stabilize at 0 until you hit that 11th degree polynomial that's in there, right? But I do know this. Right. I mean, that's certainly true. Is that clear to everybody? Right? Because certainly all the stuff generated by degree 3 or more contains the smaller stuff. Right? Now, not helpful so far because these are ideals of Rx. Right? And of course, I should point out these are all contained in A. Well, so somehow I need to use the fact that R is a theory. So I'm going to kind of use this to get ideals down in I need to get ideals down in R. Any ideas how to do it? I'm going to build an analogous chain of ideals here in the following sense. It's not associated ideals I am R. So here's what I'm going to let I n do. In is generated by alpha n, such that alpha n is a leading term of degree n or less element or 0. Right. So these ANs are set up with generators, right? And of course, they can stabilize for a while. But so you've got a set of generators for A3, set of polynomials that are degree 3 or smaller. A4 is degree 4 or smaller in there and so forth, right? And what I'm going to do is I'm going to take the leading terms of all of these elements of AN, and I'm going to let that be IN. Correct? Now, let me point out what we have here. Claim for all n, each IN is 9. Well, notice that if alpha and beta are leading terms, say F B 3 less than or equal to n or 0, then alpha plus beta. Of the degree interval. And of course, the leading term of 0 is 0. I know that's kind of a silly thing. Can somebody justify this? Well, there's a subtlety there. Yeah.
X to kg because we need to make sure.
Right. So if degree of f and g are the same, then it's just add them up, right? No problem. What if, for example, the degree of f is 5 and the degree of g is 2? Looks like you're in trouble, right? But you're not, because all you have to do is multiply this by x cubed. And now this is the leading coefficient of degree 5, and so you get the output. Everybody okay with that? So let me put that mark and multiply by x n, or let me say x that to adjust. Right? And the other one's easier. Then R F have leading term. So each IN is an ideal. Everybody okay with that? Okay, so now I feel like I put a move on this thing, right? I'm getting there. By the way, I also am going to make this claim here. And that is that, okay, so these are all ideals. I claim that IN is contained in IN plus 1. How can somebody justify that? Why do I get this contained in here? It's the same thing. So take something, well, of course, if you have something, the leading term, polynomial degree n or less, then it's certainly a degree n plus 1. That's right. So now we've got this on the ropes. I feel like, well, whatever the opposite of all is. And I know that this is Noetherian, and so it must hit a stabilization. So this is, so we're going to say IN plus K is IN for all K. Right, so from here on, it's all IN. And let me make another observation, and that is each IK is finite interval. So let's say R or 1K or zero to only. I think all of the things maybe 0, maybe 1, K. So I know that each of these, and of course these subscripted elements are generate this ideal. All of them are finite generated. For each R K L, find F K L in A, such that the leading coefficient of FKL is R. And I claim that A is generated by, I guess I have to start this at 0. F 0, 0, F 0, 1, F 0, I0, F 1, 0, F 1, 1, F 1, I1, comma, F N 0, F N 1, F N I0. Looks like a long list, but there's only finite many of these, right? And so hence it would be in theory. Now, can anybody justify my claim? Let's see, I don't really think we need to, actually. Because as long as we know that these IKs are generated by these, I think, because if the degrees are short, then you can kick them out. As long as, oh, I see what you're saying. Yeah, and so I want the degree of all these. Each F, you're right, I should be careful about this. KL is less than or equal to K. Yeah, I want it that way. Yeah, I don't want to spread out and get like something that's way too big. Okay. So here's where I'll get a little hand wavy. So write everything down. But why should this generate? That's right. Like suppose that you have an element A in A of degree n plus 1, right? The leading coefficient, look at the leading coefficient of this thing, right? This leading coefficient can be generated by elements actually of, what did I call it? I sub n, right? Because this degree 1 n plus 1 polynomial has the same leading coefficients as this, right? So take that leading coefficient. You can write that leading coefficient as a sum of these constants that generate In, right? Well, instead of using those constants, use the polynomials, right? Match it up and then subtract. And what happens when you subtract, you now have something smaller in A of degree n. Everybody agree with that? Okay, so now you're down to degree n. Its leading term is also a sum of these. So use these things to wipe out that leading term, and now you drop it to degree n minus 1. Right? But that's okay, because that leading term of n minus 1 is generated by something in n minus 1 by definition, because it's still in A, so its leading term has to be generated by these finite generators. So take these Fn minus 1s that match it and drop it, and actually you can do a pretty efficient induction argument just by dropping the degree like that. So there you have it, right? It's Noetherian, and these will work. These big ones can drop everything down to degree n minus 1, and once you're down to n minus 1, you drop to n minus 2 and cascade it down. Where did I use the fact that brain has an identity? It must be in there somewhere, right? Because of the Gilmer condoms. I can think of a couple of places. Does anybody see? where we use the identity?
You had to multiply by x.
Several places, right? First of all, there was proof that this thing were actually ideals, right? Because remember, back here, if our leading terms were off by a degree, I could fix it by multiplying one up by an x to the n. You don't get this unless you've got an identity. And number two, in the final bit of the proof, where I was a little bit slipshod, basically, if you wanted to generate something up here, you might have to multiply by powers of x to make the degrees match. So you need powers of x to make this machine go. And it's very subtle, right? At first blush, you might not notice it, but there it is. And it's incredibly important because it ain't true without an identity. Okay, any questions? Okay, the next brain tickler I've got to ask you is, what about power series? I mean, well, I used to have that theorem up there, but the Hilbert Basis Theorem is also true for power series. And I'm telling you, that ain't gonna work, right? I don't expect my power series to have a degree, right? How do we do that? I'm gonna take, actually, the power series version, in a certain sense, well, I don't know if it's easier or not. I think it's a little bit easier maybe, but it involves, to be really complete, it involves the actual choice. So I'm going to get you a little ways into it and kind of say, well, here's where you make a choice. So we'll continue our schedule proof for 2 power series. Okay. So here it's actually kind of a different pack than this. For the Hilbert Basis Theorem, I use degrees, and basically I use the fact that you can kind of, I mean, I wouldn't call this a division algorithm. That's essentially what I did, is I used the fact that the leading coefficients form finitely generated ideals to drop degrees. I'm going to do something different here. For power series, it suffices to show every prime ideal. Okay, so here we're using some tools we've already developed, right? The theory means every ideal is finitely generated, but that's equivalent to every prime ideal. So this is going to make my life easier, and you'll see in a couple places where it makes my life easier, because all I got to do is check the primes, all right? So to this end, yeah. Oops. I want some prime ideal. I suppose it's a prime ideal. Prime ideal. It's spices. Yeah. It's fine. Okay, any ideas? Any brainstorming on this? Okay, let's break this up. 2 cases. Let me make it honest. There are 2 things that can happen. X is in gamma or X is not in gamma. Suppose that X is in gamma. I claim there exists, an ideal P R such that, so this is an ideal boundary. Yes. Well, actually, people all do is, problem with intersection is, let's do this. Fine. And as I pointed out, this is the only thing that we can plug in. Notice that, since is in gamma, and the kernel P is the ideal term by X. Right. That's pretty clear, right? Isn't it that the kernel P is generated by X? Because the only way this is going to zero is the constant term is zero. If the constant term is zero, it's got to factor X. Then the image of gamma in R is a the fact that it's prime comes from the correspondence theorem, right? Why is it proper though? Let's make sure I've got all my ducks in a row. How do I know this is proper?
Contains a unit that.
That's right. If the image of this, if the image of gamma zero, such that that in that of gamma is proper. Because if not, then there exists f of x in gamma such that f0 equals 1. And what's the problem here? I haven't given you the theorem formally, and I'm going to, but power series, but I haven't even remembered this from what happens when you have a power series that has unit term or unit constant? It's invertible. So that immediately gives you this image in R is actually a proper prime ideal. Notice that as R is Noetherian, P is equal to alpha 1 alpha. Generated, therefore, the original gamma. Well, I claim And let me verify this for you. Certainly. Well, actually. Let me go this here. For this direction, it suffices to show that each of these alphas is in gamma, because I already know that X is in gamma by assumption, right? Well, if, let's say alpha J, notice that alpha J is F of zero for some F of X in gamma. So I can write F of X as alpha J plus V1X plus V2X2 plus whatever power series. And this is in gamma because F of X is therefore alpha J, which is F of X minus X comes V1 plus V2X plus is in gamma as F of X and X. So each alpha J is gamma, and so we have that completed. For the other container, we need to show that gamma is contained in that. That is, everything in gamma can be written. That's probably even easier because what F of X being gamma, right? Then F of 0 is gamma in R, and gamma is the sum of R I alpha I. Right, because that gamma lines down in that gamma is actually an element of this prime ideal P, so it's a linear combination of these alphas, right? And so F of X, I don't know much, can be written this way. And this piece is in alpha 1, alpha K, and this piece is in X. So in the first case, we get, if X is in gamma, then we get that your prime ideal is finite and generates, and for A for us, right? The next question is, okay, Jim, put your money where your mouth is. What happens if X is not in gamma? And this, I think at this point, you're actually going to see the importance of this characterization of Noetherian rings in terms of primes. That is, you're going to see in this part of it that it's important that we're able that we only need to check the primes. Okay, right. So now again, and E of gamma, X. Let I Now, let me take a little aside here. Here's the wonderful weird world power series. Great, I love it. One and only one of these are both irreducible polynomials. Let's just say over the end, right? I'll let you easy. These are both irreducible polynomials over the end. Degree 1, right? So the only thing you could ever do is pull a constant out and, hey, look, they're monic, so you're not pulling any constants out of that, right? What are their status? What is the status of these two in the power series? In the power series, that factors into two irreducibles, but I don't know how to do it. I'll show you. And this one's irreducible. Weird, right? Let me show you how to practice it. And here's what I mean by I don't know how to do it. I'm being a little bit flippant when I say that. So, suppose you almost done. Right. Now, the question is can I continue or not? Well, okay, so what do I got to do now? Well, I've got the constant terms matched, but I need to find A and B such that 2B plus 3A is equal to, in this case, 1. Can I do that? Those two integers are relatively prime, so indeed I can do that. I could do, for example, I don't know, B equals, let's go, plus B equals 5. So it's somewhat arbitrary. And A equals what they. Everybody okay with that? Getting closer. And I can use this process indefinitely. You know, here's why. Right? Now I need the next term to be 0x squared, right? So ax squared plus bx squared. And how do I know I can do this? Well, I know I can do this because, for example, I get along the way minus 15x squared. And so now my task becomes I need to have 2b plus 3a minus 15 is equal to 0. Or in other words, 2a plus 3b is that. But again, 2 and 3 are relatively prime, so I can actually generate any number this way. Right? So now I throw in the solutions to this, right? Maybe I'll do concrete solutions again. What do I need? 2b plus 3a is equal to that. Move my things here. I want to be lazy and call it 0. And so my 3a would be 5. Right? And now, again, right, get all the middle terms up. And in this case, we'll get to like cube. I'm going to have 25x cubed and then 0, and then plus 2b 2b plus 3a. And now I just have to solve this for negative 25. Now I can't write down what all these are. Maybe there's some kind of algorithm I can do some kind of recursive thing. I can't figure out how to do it now. But these factors, even though, and notice that if I pick different solutions at the beginning, it might sort of change what's going on there, which is kind of wild and wacky. But probably not too surprising, because of course I can multiply this by a unit, which is any power switch starts with 1, and jiggle these all up. I think that's a professional term, actually. So anyway, this will factor, right? This will not. Because once you try to factor this, your hand is tied up to signs. That's the only way to do that. Because if I go before one option, then that makes one of them a unit, right? And now I'm totally hosed because no matter what, the linear term has to be even, which is impossible, right? So there's strange things that can happen in power series. And I'm coming full circle here because there was a point called this. It turns out that the power series ring over Z is actually UFD. It's got unique factorization. So this is a prime element in that ring. If you do this phi map here that we've been talking about, the ideal 4 plus X, this will just be 4. And the reason I illustrate this point is, even though this generates a prime ideal up in power series, its image down here is not prime anymore, right? So after all that, the point is this I here, it's the image of the prime ideal gamma, but there's no real reason to suspect that it is prime, right? But it is finitely generated, right? So at least I can do this. Now, this I'm going to get a little flaky here because, like I said, the axiom of choice is necessary. I'm going to explain this sort of like peeling off, right? So I claim, so find, let's say F1, F2 of Fk in gamma, such that Fi of 0 equals alpha. So these are just numbers. These are just elements of R. So there's no real reason to suspect that these things are actually in the original gamma, right? But I mean, this thing basically makes like Henry VIII, cuts the head off, right? And that's what you've got right there. So I can put the body back together and find this alpha 1 that it came from, F1, alpha 2 that it came to, and just pick these. By the way, there could be a boatload of these. There could be uncountably many of them. Just pick one. Pick one, any one. And I claim now the gamma is generated by F1, F2, and if I can establish this, then that finishes the theorem, right? Because now I've shown that whether gamma contains X or whether it does not contain X, it's finitely generated. Now, how is this going to work? Well, here's where I'm going to get a little funky on you. Pick your favorite element of gamma, and we'll assume it's non-zero, fine. And we'll write it this way. Well, let's write gamma. It's gamma is 0, gamma is 1, X, gamma is 2, X squared. Now, here's how I pull this apart. Notice that gamma 0 is in I, right? Because if I plug in 0 to that, I get gamma 0, that drops down into the ring, and that's an I. So I don't know much, but I can write this as gamma 0 is A01 alpha 1 plus A02 alpha 2, A02 zero K out. So what I'm going to do is notice if I have A01, F1, A02, F2, A0K, Fk, then this is in gamma and has constant time. In zero. Agree? Because that's a linear combination of these power series that I know are all in there. And it has constant terms. So if I have gamma x minus whatever this is, the constant term here is subtracted off here. And so basically what this is this is an element in gamma, because gamma x is, and because that's linear combination of the epsilon, and it is zero for a constant term, because it'll essentially cancel out the constant term, right? So I don't know much, but this is x A1 of x. Agreed? And this is the key. This is in gamma. And in fact, I guess I could generalize this to xn, right? Because there's no next terms in there, but so maybe there's a bunch of zeros, but it doesn't matter. That's in gamma, right? But x, not in gamma. So xn is not in gamma. Because gamma is a prime ideal. H1x. So now, what you can do is you can do the same thing. H1x is let's say I'm going to P0 P1x P2x squared. And you can repeat the process. So find let's say A11 A12 A1K such that A11 F1 but one F1 minus A22 F12 F2 minus A1K Fn X has zero constant. And so now what you've done is now you have this is xn times right. So what you now have is you now have xn times you can replace this by this difference here. So now what you've got is you swap out the next term. Now this actually takes the action of choice to do this carefully, but we're running a long time, and that's basically the end. So basically, intuitively, in fact, you might try this. It's easier to sort of visualize with a principal ideal. But what you're doing is you're peeling off every time, and these A00, A11. So the power series that you need to generate is gamma X. The multiplier of F1 will be A01, A11X, A12, and X squared, and so forth. And so basically what you're doing here is you're building the coefficients that you need to generate. Okay, any questions? By the way, did you see it again? The need for the identity? All right. In the first case, the ideal was generated by alpha 1, alpha 2, up to alpha n, and X. If there's no X, you're in trouble. And X is once again used over and over here. So once again, you need that identity here to make a machine run. Okay, any questions on that? All right, well, I encourage you all to be at the math club this Friday if you can. Raphael's going to talk to us. Actually, looks like cool stuff. Error correcting codes and security and all the kind of math. And he's going to do it with polynomials, which is quite the feat. So, all right, any questions? All right, I'll see you on Friday.